Good evening, everyone. My name is Ken Pasakyan. I'm here to do task 2. Uh, this is about the key mapping. So it's task 2 is about designing a circuit that can be built using a NOT gate only that will output logic 1 whenever the 4-bit hexadecimal is an even number from 2 to 10. Use the information above to create a truth table. Draw the K-map from the table data. Draw the design using design. Draw the design circuit using logics only. So this is the so first let's go first for the truth table. This is let's go to for the truth table first. So this is the truth table of the uh, for task 2. So it's 4-bit hexadecimal. So the inputs are A, B, C, D, and 1 bit. So it's going to be have an output that is Y, but 1 bit output Y. So only for even numbers. So that except for 0, because 0 is 0. For 1, we can 1 here. 0, 0, 1, 0. Then this is because it's an odd. So now for the even number 2, it's still 0. For 3 here, it's 0, 0, 1, 1. It's gonna be still 0. For an even, it's still gonna be 0 because of the inputs. So 5 is an odd, it's going to be 0. So let's go to 6. So 6 here is 0, 1, 1, 0. It's going to be 1. That's the output already. It's an even. 6 is the even number. For 7, it's an odd. It's going to be 0. For 8, here it's 1, 0, 0, 0. It's going to be 1. So for 9, it's going to be 0 because it's odd. It will be 1, 0, 0, 1. And for the last one, up to 10 is 1. It's going to be 1, 0, 1, 0. So for the others, up to 15, because this is a 4-bit hexadecimal, it's going to be up to 15. So it's going to be a 4 by 4. Here, for the rest, it's going to be still 0. Now for the K mapping, here's the K mapping right here. So Y, A, B, C, D. So it's going to be 6, 8, and 10. So here it is. Because 6 is 0, 1, 1, 0. So it's gonna be complementing B times BC complement D plus 8 is 1000. But A is A times B complement times C complement times D complement right here. Now for 10, A complement B, C and complement D. This is the K mapping right here. C complement B complement C complement D, C D, and C complement D. This is the placement 0, 1, 2, 2, 4, 5, 7, 6, 12, 13, 15, 14, 8, 9, 11, 10. So the only one that has a 1 is right here. Going to be 6, 10, and 8. So so for the simplification, it's going to be this. It's going to be A, B complement plus A complement B C D complement. So this is the ordinary. This is the logic circuit right here. This is the equation equals logic circuit here. So for the equivalent, so that's going to be a NAND gate only. Actually, I'm using inverters so that it will have the same result here. This is gonna be the NAND gate right here. So now next, let's show the result for the simulation again. So here it is. I already tested out. This this is what it looks like. So this is the simple one. It's only using AND gate, NOT gate, and OR gate. This one is using NOT gate as inverters, and this is a NOT gate, NOT gate, NOT gate. This is a NOT gate to create a OR gate. So let's simulate. So first, let's try 0, 0. That means here 0, 0 in the input, all 0, 0. So let's 0, 0 hit 0, 0. As you can see, the display is 0. Um, it's the same input, gonna be 0 also. The display is also 0. That's why it's red. Now let's try for the other event. The event number 2, but it's still 0 right here. Let's go for, it's going to be 0, 0, 1, 0. So 1, 1. Still gonna be 0 display. Now let's try for the other one. Let's try for all add, but some of the event are still 0 because of the inputs. So for, let's try for the even number that has an output of 1. So here, this is gonna be 6. Let's see. Let's try for 6. It'll be 0, 1, 1, 0. So it's going to be 1 here because A, B, C, D. B, B should be 1. As you can see, it's on. Let's try D, not D 1. As you can see, it's also on. So let's try for the other one. The number 8 is gonna be 1, 0, 0, 0. So let's see here, 1 here, and all of these are 0. 0, 0, 0, 0, and as you can see, for the simple one, for the other logic gate, only AND gate, it's 1. Now for the NOT gate, it's also the same. So this is the, now for the last one, the other is 10, 1, 0, 1, 0. So let's try it out. Let's change Z, letter Z to 1, and also 1 here. Yes. As you can see, it's still green. That means the display is still 1. Now let's try for the other even numbers. That's gonna be 12. So we 1 1 0 0 1 0. As you can see, some of the even is red or means 0 display because we're only up to 10 even number from 2 to 10, but 0, 2, and 4 is not is also displayed in 0 because of the input. So that's that's it for task 2. Um, using going for the making a logic gate of having an output of 1 only using NAND gate, having a 4-bit hexadecimal from even number to 10, and drawing the K map from the truth table and getting the simplification using the K map. So that's it for task learning experience. This K mapping is actually uh, for me, it's still hard to really apply in simplifying the equation, the binomial expression. So it's still hard to do, but it's still amazing to apply because once you learn it properly, it's going to be easier to convert or to simplify the polynomial equation, I mean expression. So that's my learning point here, and that's all. Thank you.